Hello, students. Welcome back, ladies and gentlemen. And today we are going to be starting and finishing our notes all in one day so that we can actually do things the next 2 days. But this topic today, you really have to ask yourself, well, does it really matter? Some of you might be thinking, does it matter? The answer is, it sure does. Everything matters in science, especially matter, because this is where it all starts. With physics, with physical science, it all starts with matter. If we don't have a basic understanding of matter, then nothing really matters at all. So let's stop the semantics and let's get busy with what matter is. And not that scene. Let's go to another scene here. Our control room is going a little haywire here. So what is matter? Let's take a moment and let's go around the room. And I want you to try to give me some examples of what you think is matter. Take a moment. What is matter? All right, well, let's define it. Matter is anything. All of those things mentioned and everything else that could be mentioned, essentially, except for intangible things that don't have mass and volume, like your thoughts, perhaps, or your emotions. Do they really have mass and volume? Well, maybe we could get into a physiological debate about that. But any object you could possibly mention is made of matter, because matter is anything in the universe that has mass and volume. Two words that we're going to be talking more about here in just a moment. But all matter, as far as we are going to be discussing in our class, there are 4 properties of matter. So let's go through these 4 properties of matter, beginning with mass. Something we've mentioned before, and all matter possesses mass. So what is mass? Well, mass, oh, by the way, let me interject a little question here. Can anyone tell me what tool is used to measure mass? If you said balance, good job. If you said scale, we'll get to that in a little while. But mass is measured by a balance. And mass is the amount of matter in an object. So, for instance, I have a lot more mass today than when I was your age. In fact, you could say I'm rather massive because, well, I have a lot more matter in my body than I did when I was your age. All right, we won't get too far into that subject, but I'm more massive than you. And mass, here's another little question for you. What is the basic unit of mass in the metric system, everybody? Good. Gram. Mass is measured in grams, abbreviated by a G. And remember, in the metric system, all you have to do is add prefixes like milli or kilo in front of the basic unit like gram to get a whole different unit of measurement. So a milligram is 1,000th or 0.00 grams. And what do you think a kilogram is? 1,000 grams. In fact, I have a kilogram right here. This object, this brass mass, has a mass equivalent to 1 kilograms. In fact, you might even be able to see the symbol on it. 1 kg for kilograms. All right, what else about mass? Well, this is interesting. Mass does not change relative to its position in space. So if my body has a certain mass to it, or let's take me out of the equation, let's use this brass mass. It's a kilogram. We have this kilogram here in White Township, New Jersey. What do you think the mass of this object is if we were to take a trip to Florida? If you said 1 kilogram, you're right. Its mass does not change from New Jersey to Florida. But what about if we were to take it into space? Bring this mass up to the International Space Station. What would its mass be up in space? What do you think? Say it out loud. Take a guess. Interesting. Well, the actual answer is 1 kilogram. Its mass does not change relative to its position in space. Now, some of you are confused, and what you might be thinking of is our next property of matter, which we'll get to in a moment. So hold on to that frustration you might be experiencing right now. But understand that the amount of matter in an object does not change from place to place. 1 kilogram mass here on Earth is 1 kilogram mass in space. It does not change from one place to another. However, what you might be thinking of is weight. Weight is gravity's force of attraction on an object. So let's take a little rubber ducky here, for instance. On Earth, this little rubber ducky might have a mass of, say, 10 grams. But if we send this rubber ducky and its little space shuttle, whoosh, out into the far reaches of space, does its mass change? No, its mass does not change. It still has a mass of 10 grams. But its weight does change because gravity is pulling on it differently. Now, the weight of an object is measured in a new unit that you are not familiar with yet. It's measured in a unit called a Newton. Now, when we say a Newton, we're not talking about fig Newtons here, okay? Not fig Newtons. We're talking about the Newton named after Sir Isaac Newton, a great scientist we'll learn about later. But a Newton is a measure of gravity's force of attraction on an object. So the stronger the gravitational pull on an object, the more it's going to weigh. The weaker the gravitational pull on an object, the less it will weigh. That's why our little rubber ducky here weighs less in space because it's further away from the Earth's surface. The closer to Earth's surface, the more it weighs. So now get a load of this crazy thought. In White Township here, we have different elevations. Here at the school, we're maybe 300 feet above sea level. You go to the top of the mountain and you're almost 1,300 feet above sea level. It's about 1,000-foot difference. And I know I'm using dirty words here in science class, but I want you to understand the concept here. You have an idea of what a difference in 1,000 feet is. Did you know that you weigh less at the top of the mountain than you do here at school? Or, to put it in another frame of reference, go to Freedom Tower in New York. You weigh less at the top of the building than you do on the ground floor. It's true. It's true. The farther away from the surface of Earth you go, the less you weigh. The closer to the surface you go, the more you weigh. So if you want to lose weight, as so many people do these days, but you don't want to lose any mass, just go somewhere far away from the Earth's surface. In fact, if you're an astronaut, no matter what your mass is, you will be weightless and you will be able to float through the space station with the greatest of ease as if you were flying, because you are literally lighter than a feather here on Earth when you are weightless in space. So weight is something that can change relative to its position in space, because weight is dependent upon the force of gravity pulling on you, and that gravitational force does change from one place to another. I know it's kind of funky to think about, but your weight changes, your mass does not change. All right, let's move on to the next one here. Volume. Volume. Speaking of space, my volume is larger than your volume because I take up more space. I'm bigger than you. Volume can be described as the amount of space occupied by an object. The bigger the object, the bigger the volume. I have a greater volume today than when I was your age, simply because I'm more massive today than I was when I was your age. Why is that? Because I love ice cream. That's why I love ice cream and chocolate. I love ice cream and chocolate. That's why my volume is bigger and my mass is bigger. But volume, you may remember from last week what the basic unit of measurement is in the metric system. And boy, I gave you the answer there. How about I hide it for a moment? What is liquid volume measured with in the metric system, everybody? Yeah, liters. Solids are measured in cubic centimeters. Remember, we talked about the difference between solids and liquids last week. And also, if some of you got a bonus point for finding the error in one of the videos last week, I was holding up a thermometer and said milliliter. That was wrong. Some of you got the right answer. We measure temperature in degrees Celsius, not milliliters, silly. But back to volume here. Liquids are measured in liters, and remember, you can add prefixes in front of that basic unit like milli. So a milliliter is 1,000th of a liter. So if we had a container like this one, this container is hollow, could be filled with a liquid, and it would be 1 liter or 1,000 milliliters. That's an equivalent measurement to a solid that has 1,000 cubic centimeters. But because this is a solid, we measure it in cubic centimeters. Liquids are measured in terms of liters or milliliters or deciliters. You know, the prefix doesn't change the unit that we're working with. It just changes the amount of that unit. And remember from last week, one of the most important points here and coolest things about the metric system is that 1 milliliter equals 1 cubic centimeter. And if we're talking about water and we remove, we remove this 1 cubic centimeter. If it were hollow, we filled it with water, it would have a volume of 1 milliliter. And if we measured the Mass of it, it would be equal to 1 gram of water. 1 equals 1 equals 1. Length, volume, and mass are all connected in the metric system. It is a beautiful thing, a beautiful thing. All right, enough about volume. Let's move on to density. Density. You watched some videos yesterday with Archimedes and the fantastic way he was able to determine whether the king's crown was pure gold or not. You also watched the video about the ship, that gigantic Titanic-sized ship that was able to float because of this word density. Density is described as the mass of something per unit volume. Mass per volume. Now, I want you to look at this word here, per. I know it sounds like a happy kitty cat. I can't purr, but if you have a cat, you know what I'm talking about. That's with a U. This per has a mathematical meaning to it. Call it out if you know what the word per means in mathematics. If you said divide, then you are right. The word per means divide. So mass per volume. I want you in science, especially this first marking period as we're learning about physics, to really look at words and think about their mathematical meaning. Mass per volume is telling us what the equation is for density. Density, there is an equation for it. Density is equal to the mass of something divided by its volume. So mass divided by volume is equal to density. So Archimedes was able to determine the density of different substances like gold. And if you can measure its mass and measure its volume, then you can determine its density no matter what shape it might hold, whether it's a block or a blob. If you know the density of a substance, then you can identify that substance by calculating its density. We're going to be doing that over the next couple of days. But first, let's finish this up. With solids, remember, solids and liquids are expressed differently in terms of volume. Likewise, their densities are expressed a little bit differently. For solids, density is expressed with the units grams per cubic centimeters. So if we see that something has a density of grams per cubic centimeter, then we know we're talking about a solid. If, however, we see the units are grams per milliliter, then we know we're talking about the density of a liquid, because liquid density is expressed in terms of grams per milliliter. They're both essentially the same thing in terms of mass divided by volume, but remember, volume is expressed differently for solids and as for liquids. So solids, density, gram per cubic centimeter, liquids, grams per milliliter. Now, before we leave today, there are a couple of other words that matter, a couple other terms that matter. The first one is inertia. Inertia is something we all possess. Inertia is kind of a cool word. I wish I could demonstrate this to you a little bit easier. But how many of you had difficulty getting out of bed this morning? How many of you needed someone to push or pull you out of bed this morning because your alarm clock just wasn't enough? Well, you had inertia. You see, inertia is the Latin word for lazy. If you are lazy, then you have inertia. Now, before you put your nose in the air and say, I'm not lazy because I do my work when I'm supposed to, and I'm very diligent. Well, that may be the case, but you're still lazy from a physics point of view. Because inertia or laziness has to do with an object's resistance to motion. And we all have that, like it or not. No matter how highly motivated you might be, you still have inertia. And to prove it, think about this. If you were riding in a car and you were the passenger, what is the first thing to do that you should do before the car starts moving? If you said, put your seatbelt on, that's right. You got to have your seatbelt on for safety. The reason for that is inertia. Now, think about, this is a thought experiment. Do not actually do this. But if you were the passenger in a car and you didn't put your seatbelt on, and the driver was going really fast and then slammed on his brakes, do you know what would happen to you as the passenger? You would go right through the windshield, and that would be the last thing that you ever did. That would be a very tragic accident. Why? Because even though the car might stop, you still have inertia. And if you're not held on to that car by a seatbelt, that inertia that you have allows you to keep on going until you're stopped by another force, namely the windshield or the road in front of the car or the brick wall that you've just driven into or whatever the other object might be. So inertia is an object's resistance to motion, and we all have it, like it or not. And we're going to get back to inertia when we talk about motion next week. But that is one other word that you should know. Another word that you should know, another word that matters, is something called specific gravity. Now, specific gravity is a comparison of a substance's density to the density of water. Now, I'm not going to elaborate on this at all right now because tomorrow we're going to do a little class activity together, and you are going to calculate the density of water. And then we'll be able to talk about specific gravity a little bit more. But I want to make sure that you have this written in your notes for now so that we can talk about it a little bit more thoroughly tomorrow. So a couple other terms that matter: inertia and specific gravity. Comparison of a substance's density to the density of water. Now, we're going to call it quits there for now. And tomorrow and the next day, we're going to be doing some activities together in our virtual lab, but you will need to be paying attention both visually and audibly to participate in these activities tomorrow. So for today, I'm going to say bye-bye and go back to your one-stop shopping for science information, Google Classroom, and continue with the next item on the list. Bye-bye.